The second derivative can be used to determine concavity. Let's see how. Provided for us is a graph that is concave up. Let's study the graph. Begin by drawing tangent lines on the left side moving towards the right. Let's draw a tangent line at the upper extreme. We can eyeball it and say that this is definitely a negative slope, and it's probably pretty steep. We'll say the slope is probably like -7. Traversing along the curve, let's draw a tangent line a little bit further towards the right. Here, the tangent line is not as steep, even though it is still negative, and it looks like it's about a -3. Now we'll go to the turning point or the extrema, and here the tangent line is obviously 0. And let's note that to the left of 0, the first derivative is negative. Now we'll move to the right, drawing a tangent line. The graph is upwards, and so here we can say that the slope is probably something like 1. Then continue to move along the graph and draw a tangent line here. And that's a little bit steeper. Let's observe that tangent lines to the right of the graph are all increasing, so their sign is positive. Now let's note that as we move from the left to the right, the -7 to -3, the value is increasing, so the first derivative is becoming a larger value. Continuing to the right, the 0 is greater than -3. Continuing to the right some more, 1 is greater than 0. And then finally, the last point where we drew the tangent line, we got a 4. That is, the second derivative is positive all along this concave up graph. Let's repeat the process for concave down. We have a graph that looks like a portion of an upside down parabola, and we'll draw a tangent line starting at the left endpoint. Starting here. That's a pretty extreme rise upwards, and so we'll say that the slope looks like about a 7. We'll continue to move to the right a little bit more, and notice that the tangent line here is positive, but probably not as steep. We will draw a tangent line at the turning point where we see the tangent line would be 0. Notice that the slope is +7, +1. So to the left of 0, the first derivative is positive. Move to the right of 0. Let's draw a tangent line. We observe that this is pretty steep and negative. We'll say that that slope looks like about a -1. And then finally, let's pick one last value, and we'll notice that it's negative, and it's a lot steeper than the previous point, and it looks like about a -5. Now, as we look at the slope values we've estimated, to the left of 0, the first derivative is positive. The values are positive and decreasing. And to the right of the 0, the first derivative is negative, and let's observe that the values are negative and getting increasingly smaller, another way to say decreasing. And since the rate of change of the first derivative is decreasing, the second derivative is negative for the concave down. Example 3. For the graph of y equals f of x given, determine the intervals where the function is concave up and where it is concave down. The graph given has 2 turning points. It begins to rise in the third quadrant into the second. It has a turning point in the second quadrant that corresponds to the x-axis value of -2. It bends downwards and then intersects the y-axis at 3 and then continues to rise into the first quadrant. To determine concavity, we must determine the values on the x-axis where the direction of the cave changes. For this graph, it rises from -infinity. It has a turning point at x equals -2, but the bowl changes directions at x equals -1. So by the shape of the graph, we conclude that the function is concave down. That is, it bowls downward or bends downwards from negative infinity to negative 1 along the x-axis. Test for concavity. A function f is concave up on an interval I if the first derivative f prime is increasing on that interval. That is equivalent to f double prime of x greater than 0, or the second derivative positive on that interval. A function f is concave down on an interval I if f prime, the first derivative, is decreasing on I. That is equivalent to f double prime less than 0, or the second derivative is negative on that interval. Example: for the function f of x equals x to the fourth minus 6x squared, find the intervals where the graph of f is concave upward and the intervals where the graph of f is concave downward. To determine concavity, we work with the second derivative. To get to the second derivative, we begin by finding the first derivative, f prime of x. The derivative of x to the fourth is, bring the 4 down, you got x to the power of 4 minus 1 is 3. And then for the derivative of 6x squared, bringing the 2 down, 6 times 2 is 12. X remains. We continue in this line, and the next thing we're going to do is find the second derivative. The second derivative is the derivative of the first. So the derivative of 4x cubed, breaking the power of 3 down and multiplying it to the 4, give you 12x. 3 minus 1 is squared, minus the derivative of 12x is just 12. Now we need to find where activity takes place, so the next step is to set that second derivative equal to 0 and solve. We've got 0 equals 12 x squared minus 12. Algebraically, we can factor out the 12 on the right-hand side, so you have 12 times the quantity x squared minus 1. Continuing to factor some more, we would get 0 is equal to the 12. X squared minus 1 is a difference of squares, so you got x minus 1 times x plus 1. Now we've got two factors that contain a variable. We'll set each of those equal to 0. 0 is equal to x minus 1. 0 is equal to x plus 1. And that gives us the values of x equals negative 1 and x equals positive 1. Now let's make a number line sign chart for the second derivative. We write f double prime of x a little bit above the line. I'll write x below the f double prime of x. We know that when x equals negative 1, the second derivative is 0. That's what we solved for. And when x equals positive 1, the second derivative is also 0. Continuing with this work, we've got, let's pick a number in each of the three intervals. I'll start with a number in the region between negative infinity and negative 1, like negative 2. Let's evaluate negative 2 in the second derivative. Pick any of the factored forms. I will pick the 12x squared minus 12. Negative 2 squared is positive 4. 12 times 4 is 48. 48 minus 12 is a positive number. An easy number between a negative and a positive is 0, so we'll evaluate 0 in the second derivative. You get 12 times 0 squared, which is this 0 minus 12, gives us a negative in that interval. And finally, let's pick a number to the right of 1. Let's pick 2. 12 times the quantity 2 squared, that's 12 times 4. 48 minus 12 is a positive number. So by looking at the sign chart, we see that the function f is concave up, where the second derivative is positive, and that happens from negative infinity to negative 1. Union, that's n again, from 1 to positive infinity, and f is concave down where the second derivative is negative, and that happens between -1 and +1. The graph of f changes concavity from upwards to downward at x equals -1, and from downward to upward again at x equals +1. A point where concavity changes is called an inflection point. Inflection points. If y equals f of x is continuous on the interval ab and has an inflection point at x equals c, then either f double prime of c equals 0 or f double prime of c does not exist. Note also that a partition number c for f double prime produces an inflection point for the graph of f only if f double prime at x changes sign at c and c is in the domain of f. Example, consider the function f of x equals x cubed minus 12x squared minus 5x plus 12. Find the intervals where the graph of f is concave upward and the intervals where the graph of f is concave downward and the inflection points. We begin knowing that working with concavity, we need the second derivative. To get there, let's find the first derivative. F prime of x is equal to the derivative of x cubed is 3x squared minus the derivative of 12x squared. We bring the 2 down and multiply it to the 12, so it'll be 24x. Then minus the derivative of 5x, which would be just minus 5. The derivative of 12 is 0. Continuing, let's go to the second derivative, f double prime of x. The derivative of 3x squared, bringing the 2 down, is 6x, and the derivative of 24x is just 24. The derivative of the constant 5 is 0. We need to set the second derivative equal to 0. So 0 is equal to, let's go ahead and factor out the common 6, and we get 6 times the quantity x minus 4. Continuing to solve, we get a critical value of x equals 4. 4 is in the domain, the second derivative equals 0. We're good to go. Now let's make a sign chart for the second derivative. I'll do f double prime of x slightly above the number line. I'll write x below and indicate that when x is 4, the second derivative is 0. Let's pick a value in one of the two regions. I'll start with the first one to the left of 4. How about 0? I will evaluate 0 in the second derivative. So 6 times 0 is 0. 0 minus 24, that's a negative. Let's pick a number to the right of 4. For example, how about if I pick 5? Then we can do 6 times 5 is 30. 30 minus 24 is positive. The sign chart of the second derivative determines the concavity. So by looking at the sign chart, we conclude that f is concave down where the second derivative is negative. So that's negative infinity to 4. And f is concave up where the second derivative is positive, and that's from 4 to infinity. We get an inflection point where concavity changes. Concavity changes from down to up at x equals 4. So the inflection point, remember a point means ordered pair, we have one of those, is going to be 4 and the function evaluated at 4. So you need to compute 4 in the function, which would be 4 cubed minus 12 times 4 squared minus 5 times 4 plus 12. And that's negative 136. So the inflection point is the ordered pair 4 comma negative 136. Example. The function f of x is continuous on negative infinity to infinity. Use the given sign chart for the second derivative of f of x to find the inflection points of f of x, if any. The sign chart given depicts second derivative, that's f double prime of x, drawn above the number line and x written immediately below it. For the x value of 1, the second derivative is 0. For the x value of 4, the second derivative is undefined, and for the x value of 5, the second derivative is 0 again. From negative infinity to the x value of 1, the second derivative is negative. Between the x values of 1 and 4, the second derivative is negative. Between the x values of 4 and 5, the second derivative is positive. And where x is greater than 5, the second derivative is negative. Inflection points occur where the function exists and the second derivative changes signs. So we have a inflection point, so we'll write inflection point for f at the ordered pair 4, f of 4, and we also have another inflection point for f at 5, f of 5. Example, the function f of x is continuous on negative infinity to infinity. Use the provided information to sketch a possible graph of the function. We'll begin with the function values using the table of values. So let's start with the ordered pair negative 3.1, comma 0. We'll just draw a dot. The next ordered pair is negative 2, 3. We have another ordered pair, negative 1, and then positive 1.9. The next ordered pair is the origin, 0, 0. Continuing to the right, when x equals 2, the ordered pair value is negative 1.4. And at x equals 3.1, the ordered pair is negative 1.8. So we're going to have to eyeball that a little bit. So we've got our function values plotted. Let's look at the first derivative, that's the f prime of x. The sign chart tells us that the function is increasing or rising from negative infinity to x equals negative 2. It falls from negative 2 to positive 2 and then continues to fall from 2 to positive infinity. The zeros tell us you have a horizontal asymptote at those points. Now let's look at the second derivative. The second derivative gives us the shape of the graph. The second derivative has the graph having concave down from negative infinity to negative 1. Concave down means it's like an open umbrella. From 1 to 2, it is concave up, so it's like a cereal bowl. And then from 0 to positive infinity, it is concave down again. We need to match those characteristics with the ordered pairs we've got plotted. So let's begin. We need the function to be concave down from negative infinity to x equals 1. The function is rising, goes through those points. Now, from x equals negative 1 to 2, it's concave up, and the function is continuing to decrease, so it should look kind of like this. And the function is going to continue to decrease, but it's also going to be concave down as well. So we have a horizontal asymptote at x equals 2, continuing to decrease and going down some more. So that's a graph that meets all of the required characteristics.